So let me start with a 2017 article published in the Journal of Economic Perspectives, written by Susan Athey and Guido Imbens, about the state of applied econometrics, causality, and policy evaluation. The gold standard for drawing statistical inferences from a sample to a population about the effect of a policy is what we call a randomized control trial. And the randomized control trials, however, pretty often turn out to be too difficult or even impossible to implement, not only for financial reasons, they're quite expensive, also for political reasons. For example, policymakers are reluctant to deny access to a control group if potential voters think that this would be a nice program for them. And so political reasons do play a role, and also ethical reasons, saying that if you deny access to something which is potentially good, like a drug, then this is unethical. And also due to the fact that the population of interest might be too small. This is the main reason why we pretty often refer to observational data in economics. So data where policies were determined in a way other than random assignment, and drawing inferences about the causal effect of a policy from observational data is quite challenging. So we need methods to solve the underlying fundamental evaluation problem. And this is what applied econometrics with respect to causality is all about. In other words, it's all about strategies to identify the causal effect, or identification strategies that allow the identification of the causal effect and to get rid of the selection effect. So that's what it is about, trying to identify causal effects. And therefore we need sufficiently large data sets. So that's something that is pretty often met now with big data available. But even if we have sufficiently rich data, then still identification is difficult. We will look at regression discontinuity, RDD designs in this course. Also, we will look at differences in differences, diff and diff in this course. And we will also look at what might be an improvement, the machine learning literature, which allows us, maybe, that's not yet completely clear, that allows us to improve the credibility of policy evaluation. So the econometric literature on estimating causal effects has been very active for over 3 decades now. And since the early 90s, the potential outcome approach has become famous, the so-called Rubin causal model. So what's the basic idea? If you participate in a program, then your potential outcome in case of non-participation cannot be observed simultaneously. That's the main insight, right? So you cannot be in both states at the same time. You cannot be, on the one hand, participant and on the other hand, non-participant at the same time. That's what the potential outcome approach tells us. And looking at a treatment and a potential outcome gives us an idea how to evaluate a causal effect. So we need something for the counterfactual behavior. The counterfactual behavior. If you're a participant, if you participate in a program, your counterfactual cannot be observed, and we need a proxy for your counterfactual. That's what is also called the fundamental evaluation problem. the fundamental problem of causal inferences, that you cannot observe the same person at the same time in different states. One method to solve the fundamental evaluation problem is the so-called matching approach, which was popular in the 90s and also in the 2000s. Based on the so-called unconfoundedness assumption, which is the identifying assumption in this case, you can measure the causal effect using the matching approach. This assumption requires that all confounding factors, so that means factors X that influence on the one hand the potential outcome Y, and on the other hand the assignment to the treatment D, so that all these confounding factors are observed. And that allows for a added identification of the causal effect. So in other words, so we have a setting where there is a binary treatment, and the binary treatment is a dummy variable that is set to 1 in case of participation or is set to 0 in case of non-participation, and you can interpret the regression coefficient of the dummy variable as a causal effect in case that the identifying assumption, which is called here unconfoundedness assumption, is justifiable. Cannot be proved, but is plausible. And to allow for that plausibility, you need a rich data set. You need a lot of X's, and you need a story that the X, on the one hand, influences the assignment to the treatment, on the other hand, influences the potential outcome. And in such a case, you can apply matching methods, right? Matching methods, that's about producing statistical twins that are comparable, and then these statistical twins behave just due to the treatment differently, right? And one possibility is the propensity score matching, PSM, and we will look at that in more detail later on. So at the moment it's just an overview. Another method that is meanwhile widespread are regression discontinuity designs, or RDDs. So the idea of a regression discontinuity design is that you have a pretty close to randomized controlled trial distinction between the treatment group and the control group. And this is due to a threshold we call the cutoff point. And to be just very brief with that, so if there is some event, like a policy decision, if there is some event, some exogenous event, some exogenous experiments, and also say natural experiment, then before the event, the outcome level of some outcome variable might be like that, and after the event, it's like that. And if you observe something like a step, right, before, after the event, that's the threshold here. And if you can see something like that in the data, RDD might be the method to solve the fundamental evaluation problem. So this is the discontinuity here. And if you see some discontinuity in the outcome variable, that's the method to choose. Well, an illustrative example of an RDD approach is the Jacob-Lefgren 2004 paper, where the treatment is a summer school, and they have rich data using an administrative data set from Chicago public schools, and they measured the outcome with respect to the math score after the summer school. And the idea is here that, well, there's an event. In this case, it's a treatment It's the summer school that has taken place, and before the summer school you have an outcome in the math score which is on average on that level, and then the discontinuity kicks in, and at best it has a positive effect if you participate in the summer school, and this is due to the fact that you participate in the summer school. If we believe in the identifying assumptions, then the summer school program had a substantial effect, raising the math test outcome score by 0.18 standard deviations. Another method to solve the fundamental evaluation problem is the diff and diff method, difference in differences, DID, which has been popular since the early 90s and is until today very popular. So it's a must have here in the toolbox of the empirical researcher. The idea is that you have a look on a program group as a treatment, and you look at the program group before and after the treatment, and also look at a control group where there was no treatment before and after, and you compare the outcome of these two groups. So the treatment group difference minus the control group difference. That's the basic idea, and there are some underlying identifying assumptions. We don't want to discuss that now. And one of the famous studies here in the field is the diff and diff study of Card on the Mariel boat lift, and we will have a look on that and also think about synthetic control. So one major drawback of RCTs might be lacking external validity, so it's only internally valid, what researchers have found out, but not externally. So you cannot learn something for other countries, for other settings, in other historical episodes. So this is a major drawback, pretty often discussed. So even if everything has gone fine, so you have a high internal validity, the causal study has been done carefully, both in analysis and design. And so what does that mean for the rest of the world? So what does it mean for external validity? And here Athey and Imbens refer to IV and refer to local average treatment effects, and we will take some time also to differentiate between always takers, never takers, compliers who are in line with the instrument. Now let's come to machine learning in econometrics. Supervised machine learning focuses mainly on prediction problems. So for a given data set with data on an outcome, which can be discrete or continuous, and some predictors, the goal is to estimate a model on a subset of the data given the values of the predictors, and this subset is called the training sample, which is about 10% of the overall sample. And this is used for predicting outcomes in the remaining data, so in the 90% of the data, and these are the samples called the test sample. And this is fundamentally different to econometrics, so there's a different approach where in econometrics we want to learn something from a sample for the population. So the target is causal inference, causal statistical inference in these observational studies. And here this is about prediction. An important difference between many but not all econometric approaches and supervised machine learning is that these supervised machine learning methods typically rely on data-driven model selection, most commonly through cross-validation. So we will do that in the course, not now, but that's just kind of teaser. So we'll also see matching approaches that rely on machine learning methods, such as lasso or random forests, to estimate the propensity score. So first, we have to understand the propensity score matching, and then we can dig into the lasso and random forest to see if there is a value added of these. So overall, we see that these machine learning methods provide an important new perspective. They provide new tools to improve the estimation of causal effects in high-dimensional settings, so with a lot of covariates, because in many cases it's important to flexibly control for a large number of covariates. And that might be the future. So you have a lot of data, big data, rich data, and you want to know more about the optimal propensity score, for example. So what are the covariates X that really influence D and the potential outcome Y? So this might be useful. So far, there are not a lot of paper out there using machine learning methods. So this is pretty new stuff. But in 2017, this was the overall assessment of Athey and Imbens, who are both leading scholars in that field.